Okay, how feels everyone? Awake and ready? Ready to what? Have fun and enjoy. Today what we're going to do is we're going to cover energy balances for open systems. And before we talk about open systems, let me remind you what the energy balance for closed systems says so we can kind of have a point of comparison. For a closed system, the basic equation said that delta E equals Q in minus work out. And remember, on the left side we had our accounts, and on the right side, we have our transfers. And one of the defining characteristics of a closed system is that you didn't have any mass transfer, so the only transfers were heat transfer and work. When we deal with open systems, it's going to be a little bit different because instead of just being limited to heat transfer and work, we're also going to have mass transfer. So when we have open systems, we need to add in mass transfer. And also remember that whereas in closed systems we dealt with amounts, in open systems we need to deal with rates. Okay? So when we have this equation here for closed systems, instead of looking at the change in energy inside the system, what we're going to have instead is the rate at which the energy inside the system changes, E dot CV. Okay? And instead of having the amount of heat transfer, we're going to have the rate at which heat transfers. Instead of the amount of work, we're going to have the rate at which there's work. But now we also need to add in energy transfer by mass. So, question then becomes, how do we represent the energy transfer by mass? Well, the key here is to remember that mass, if it's moving, has a kinetic energy, has a potential energy, and also has an internal energy. When we do it on a per mass basis, kinetic energy becomes 1/2 v squared instead of mv squared. Potential energy becomes gz instead of mgz, and internal energy becomes little u instead of big U. And we'll call the sum of those three energy accounts just little e for energy, but it's energy per mass. So that's why we use lowercase e. And the key thing to understand here is that if mass is transferring, it's bringing its energy with it. So if there's a rate at which mass is coming in, there's a rate at which kinetic energy is coming in, and there's a rate at which potential energy is coming in, and there's a rate at which internal energy is coming in. So if we go to expand this equation out, E dot CV, just like with the mass balance, that represents the rate of accumulation. Right? The difference between the rate at which energy comes in and the rate at which energy comes out is the rate at which energy accumulates. And so that accumulation is going to be the sum of all the energy transfers. So Q dot in minus work plus, we have to keep in mind, just like with the mass balance, that mass could be flowing in multiple places. So we need to sum over each of those places that mass might be coming in, sum over all the inlets, of the mass flow rate at that inlet times the specific energy of that mass, right? So if those specific energies are per mass, if I multiply that by the rate at which mass is coming in, that gives me the rate at which energy is coming in. And same thing for the exits, minus sum over the exits of m dot E, specific energy at the exits. Okay, so once again, the accumulation is equal to the transfers. So the difference between the rate at which energy comes in and the rate at which energy comes out is equal to the rate at which energy is going to accumulate inside the box. So we can have heat transfers due to heat transfer, we can have energy transfers due to work, and we can have energy transfers due to mass, because mass has its own energy. Mass has an internal energy, it has a kinetic energy, and it has a potential energy. But it turns out that it's even a little bit more complicated than that, because there's this additional part of the work that we call flow work. So flow work might be a little bit strange to think about, but it's the basic idea that if you want to blow air through a straw, it actually takes some effort to move that air through the straw. And so when you have an open system and you have mass that's flowing through it, it turns out that it takes work in order to move that mass through that system. So imagine that you have some arbitrary open system that has an inlet and it has an exit. And so you've got mass flowing in here and mass flowing out here. Okay? The way you can think about this is that it's almost like upstream of the flow, there's like a little piston that's pushing that flow through. And downstream, the flow has to act like a piston in order to push the downstream fluid out of the way. So there's work associated with bringing the fluid in, and then there's also work associated with pushing the fluid out. And at the inlet here, this is going to be a flow work, I'm going to call WF for flow work. That's going to be a flow work in. That's energy that's being done on the system, so it's energy that should be coming in. Work being done on the system brings energy in. At the exit, the system is having to do work in order to push that flow out. So at the exit, that's going to be flow work out. Okay? So the question now becomes, what is the expression for flow work? The expression for flow work turns out to be fairly straightforward. Okay, so if you think of flow work or a rate of flow work, if you think back to chapter 1, chapter 2, force times velocity is going to be the rate of flow work because there's a piston here is exerting a force. And as it exerts a force, it's moving through a velocity or a rate at which the distance is moving. So the rate at which work is being done is force times the rate at which distance changes, so force times velocity. So we can break this down. Force is equal to pressure times area. And remember that mass flow rate was equal to area times velocity over specific volume. So if we do a simple substitution, that means that velocity is equal to mass flow rate times specific volume divided by area. So putting those two things together, flow work, which was equal to force times velocity, is equal to pressure times area times mass flow rate times specific volume divided by area. Right? So there's the substitution for velocity. Areas cancel, and what you get is m dot times pressure times specific volume. Okay. So what we're going to do now is we're going to take flow work and we're going to separate flow work out from other forms of work in the energy balance equation. And if you do that, you should end up with this. All right, so this is the expression for the open system energy balance, now with flow work separated out from other kinds of work. So flow work in brings energy in, flow work out brings energy out, and then we still have a work out term for all the other kinds of work. And then we have our energy transfer with mass as well. Okay, now let's take this expression and expand it out a little bit further, incorporating the actual expression for flow work. All right, so now I've expanded out that expression for flow work, and I hope you recognize that anywhere where there's an inlet, you're going to have flow work to push the fluid in, and anywhere where you have an exit, you're going to need flow work in order to push the fluid out. So that means that you have to sum over all those inlets, the flow work terms, and you have to sum over all the exits with the flow work terms. And now what you should notice is that we have, for the flow work, a sum over all the inlets, and we also have the same thing for the energy. We have a sum over all the exits for flow work. We also have a sum over all the exits for energy. Now, that means that we can combine those into the same summation. So let's look at what that will look like. So combining those into the same summation, you should end up with m dot times the product PV plus the specific energy. So if now I expand out the specific energy into all its terms, this is the sum of m dot times PV plus U plus 1/2 velocity squared plus gz. And what you should recognize here is that you have U plus PV. Remember what that is? That's H. And that's why we keep track of enthalpy. It's because this PV term shows up whenever we do flow work. So since we end up with U plus PV all the time, we combine them together and we call it H. So let's look at what the energy balance looks like now with all the terms combined. So combining and expanding all the terms, now we see that the energy accumulation is equal to the rate at which energy comes in and out with heat transfer, work, and with mass, keeping in mind that mass also requires flow work, and that's why the U is now an H for enthalpy, because that PV term from the flow work combined with the U to become the enthalpy, and we have the same thing in the mass flow rate at the exits. Now, one other thing that I'll note is that when you look up H in your tables, it's in kilojoules per kilogram. And if you calculate V squared over 2, that's going to be in joules per kilogram. So if we want it in kilojoules, we got to divide by 1,000. So I'll often write this equation, V squared over 2,000, and for the same reason, GZ over 1,000, because then the units will be consistent with the units that we use for H in the tables in the book. And this whole equation here is our open system energy balance that incorporates the flow work. And one other thing that I'll note is that just to abbreviate this and have a shorthand, oftentimes I'll write E sub H, which I'll call the flow energy, and that's equal to the enthalpy plus the kinetic energy plus the potential energy. And that's just so that I don't have to keep writing all these terms all the time. So the key thing to note here is that for open systems, you don't use internal energy. And the reason for that is that if you have flow, if the system is open, if things are flowing through, you're going to have flow work. And if you're going to have flow work, the U is always going to turn into an H for enthalpy. So our energy balance for open systems has an H in it, which is very different than for closed systems, which had a U. And that's something to be really careful about. Anytime that you have flow, you're going to have flow work. And you're going to use it always for flowing fluids. And this is one of those things to really make a note of, and that's why I'm putting stars on it and saying it explicitly over and over again, is that there is no U in the open system energy balance. There's only an H, and anytime you have something flowing, you're going to have an H, okay? So you got to remember to keep that straight. It's a different property, still done the same way. You find U the same way that you find H, but you have H's in the open systems, you have U's in the closed systems. Okay, so that's a fairly long and complicated equation. The question is, how does it break down to simplify into more realistic situations? The first realistic situation is that let's assume that we're in steady state. And in this class, we're basically always going to be in steady state. If we're in steady state, what I hope you recognize is that there can't be any accumulation or any depletion. Right? That means that what goes in has to equal what goes out. Because if those weren't equal, then there'd be an accumulation of energy inside your box. And if there's accumulation of energy inside your box, that means that things are changing with time. It's like if you spend less than you make, then your bank account will grow over time. Okay, but if we're in steady state, then nothing can change, and so no growth can happen, no accumulation can happen, no depletion can happen. So if nothing is accumulating, that means that E dot CV has to be 0. So for this class, E dot CV is basically always going to be 0. Now the other really complicated simplification is that oftentimes we're going to have one inlet and one exit. So a turbine has one inlet and one exit, and a pump has one inlet and one exit, and a heat exchanger usually has one inlet and one exit, and a pipe has one inlet and one exit. And if you have one inlet and one exit, then your summations go away, because you don't need to sum over multiple inlets and exits because there's only one of them. Okay, and so we usually call the inlet state 1 and the exit state 2. And if you have steady state plus one inlet, one exit, then this equation becomes 0 equals Q dot in minus work dot out plus M dot times H1 plus V1 squared over 2000 plus gz1 over 1,000 minus m dot times h2 plus v2 squared over 2,000 plus gz2 over 1,000. Now notice that I didn't say m dot 1 and m dot 2, and let me show you why that is. Let's look at the mass balance. Mass balance says that m dot CV, the accumulation of mass inside the box, equals sum over the inlets of m dot in minus sum over the exits of m dot out, which in this case, if it's in steady state and one inlet, one exit, means that this is m dot 1 minus m dot 2. And if it's in steady state, that has to be 0 because nothing can accumulate in steady state. And so that means that m dot 1 equals m dot 2, which when we just have one inlet and one exit, we'll just call that m dot. Now, if you have more inlets and exits, you need to name the m dot at each of those inlets and exits because there's nothing that causes them all to be equal. So they could all be different values. Okay, so let's do a quick example. This is going to be example chapter 4, problem 24 in your book. So let's read through it together. Problem 424 says refrigerant 134A. So let's pause right there and identify our substance, which is R134A. And R134A enters a horizontal pipe. Okay, so we're going to draw a diagram. And our diagram is a horizontal pipe. So we'll call state 1 the inlet, and we'll call state 2 the exit. Okay, so refrigerant 134A enters a horizontal pipe operating at steady state. Okay, so that's some important information about the process. So we know that it's steady state. It says R134A enters a horizontal pipe operating at steady state at 40 degrees C, 300 kPa. So 40 degrees C and 300 kPa are how the refrigerant enters the pipe. So that means that T1 is 40 degrees C and P1 is 300 kPa. And a velocity of 40 meters per second. So that means that velocity 1 is 40 meters per second. And again, I want to remind you that it's really important to make sure that your velocity V's look different than your specific volume V's so you don't get confused. I always put a line over the top of my velocity V's so that I can tell the difference in my own writing. Okay, so it says at the exit, the temperature is 50 degrees C and the pressure is 240 kPa. And so that means that T2 is 50 degrees C and P2 is 240 kPa. Okay, so I'm already looking at this and I'm noting that I have temperature and pressure at the beginning, which means I have two properties, so I should be able to get all others. And I have temperature and pressure at the end, which means I still have two properties and I should be able to have and get all others. It also tells me that the pipe diameter is 0.04 meters, so D is 0.04 meters. And what I'm asked to find is the mass flow rate of the refrigerant and the velocity at the exit, and the rate of heat transfer between the pipe and its surroundings in kilowatts. So let's take those one at a time. First of all, let's find m dot at the exit. So that's m dot 2. Or sorry, it just says the mass flow rate of the refrigerant, which is good because m dot 2 equals m dot 1 equals m dot. Now, in this case, an energy balance isn't going to help us right away, but what we do have is a velocity. And remember that we have an equation that allows us to relate velocity to mass flow rate. So remember that m dot is equal to area times velocity over specific volume. Now, area is equal to pi d squared over 4. We know d, so we know area. Velocity was given in the problem, so we know that. And I guess I should write velocity 1 and specific volume 1 because I know the velocity at the inlet, so I need the specific volume also at the inlet. And I have two properties, so that means I know specific volume 1. And if you do the math on this, what you should find is that the mass flow rate is 0.628 kilograms per second. All right, so there is one part done and gone. Time to start part B. Part B asks for the velocity at the exit, v2. Well, again, note that we have a way to relate mass flow rate to velocity. And so I know that mass flow rate at 2 is equal to the area at 2 times the velocity at 2 over the specific volume at 2. I know the mass flow rate, I know the area, I know the specific volume because I have two properties, so I can get that. And I just solve for velocity, and if you do that, you should find that velocity at 2 at the exit is equal to 53 meters per second. Part C asks for the rate of heat transfer between the pipe and its surroundings in kilowatts, so Q dot in kilowatts. Okay, now this should be fairly obvious. You only have one equation that has a heat transfer in it, and that's the energy balance equation. So let's use the energy balance equation. Energy balance equation says E dot CV is equal to Q dot in minus work out plus sum over the inlets of the mass flow rate times the flow energy. Remember, flow energy was equal to enthalpy plus kinetic plus potential, minus sum over the exits of the mass flow rate times the flow energy. Okay, now we got to use our brain, so we'll go step by step through this problem and let's look at it. E dot CV is going to be 0 because we're in steady state. Q dot in, we're going to need to solve for, so we're not going to get rid of that. Work is going to be 0 because there's nothing in here that does work. There's no electric wires, there's no turning shafts, there's no moving pistons, there's no work. Okay, so our sum over the inlets turns into just a single inlet. Our sum over the exits turns into a single exit. And what we end up with is that 0 equals Q dot in plus mass flow rate times H1 plus V1 squared over 2,000 plus GZ1 over 1,000 minus mass flow rate times H2 plus kinetic plus potential. Now, because this is a horizontal pipe, we know that potential doesn't matter. We know velocity 2. We can get H2 because we have two properties. We know the mass flow rate. We know velocity 1. We can get H1 because we have two properties. We know the mass flow rate. So all you got to do is solve for Q, and you find that Q dot is equal to 6.9 kilowatts. So there you have it. There is an example of applying the open system energy balance in order to determine the energy transfers occurring in this pipe. All right, so there was an example. Let me finish by giving you some general rules for open systems. General number 1, in this class, it's always steady state. Okay, if I ever give you an exam problem and it doesn't explicitly say steady state, assume steady state. It's always going to be steady state in this class. So there's no excuse for not knowing what to do with the E.CV term. Second thing, turns out that kinetic energy is usually not super important except for certain situations. So I'm going to say that you should generally ignore kinetic energy unless the purpose of the device is to change the kinetic energy, or if velocities are known. Okay, so if you know the velocities, you might as well use them, but otherwise you can ignore kinetic energy unless the purpose of the device is to change or utilize the kinetic energy. We'll talk about what the different open system components are next time, but there are a couple of components whose sole purpose is to alter the velocity of whatever's going through it. It's a nozzle and a diffuser. And so if the purpose of the device is to alter the kinetic energy, then you should assume that kinetic energy matters. In a similar vein, you should generally ignore potential energy unless the purpose of the device is to change the potential energy. An example here would be as if you had a pump and you wanted to pump water uphill. Okay. In that case, the change in potential energy is the entire point of the pump, and so you would need to worry about potential energy in that case. And I'll also give you the same caveat, which is or if delta Z is known. Okay, so if you have the height changes in a given situation, then you should probably use them. But otherwise, you should ignore it unless the purpose of the device is to change the potential energy. And the reason that we ignore both of these is that it turns out that compared to the changes in enthalpy, the kinetic and potential energy changes are usually too small to really matter. On a similar note, you also are usually going to ignore heat transfer unless the purpose of the device is for heat transfer to occur. So for example, a heat exchanger, its sole purpose is to allow heat transfer, and so heat transfer is going to matter in that case. And I'll add the same caveat, which is or, I'll just say this, or you're told otherwise. Okay, so if you have a component for whom heat transfer is not its main component or its main purpose, but I ask you to solve for the heat transfer, then you need to assume that heat transfer is there. Okay, but in general, oftentimes when we design a thermodynamic component, if we don't want heat transfer to occur, we do everything we can to prevent heat transfer from occurring. So we insulate it or we do whatever we can in order to eliminate any heat transfer losses. There are also some other devices like nozzles where things just move too quickly through them, or throttling devices where there's just not enough surface area for heat transfer to be significant. But the general rule is that unless you're told to look for heat transfer, assume that it doesn't matter unless that's the purpose of the device. And that's it for this lecture. So the main idea, the main takeaway from this lecture is that we developed the energy balance for open systems. And what we'll do next time is we'll look at a number of different types of open systems, and we'll look at what their purposes are, and we'll look at how that energy balance equation breaks down and reduces for each of these different types of open systems that we deal with in thermodynamics. But until then, remember to have fun and enjoy, and be where you want to be doing what you want to be doing. Otherwise, go somewhere else and do something else.